I'm here to talk about the maximum modulus principle, which basically means that the absolute value of f under nice conditions cannot have a relative maximum on a sort of an open interval, open region. So suppose that we do have a maximum called a, so f of a is bigger than or equal to f of z for all z in some region close to a, sorry. I'm going to split into two cases. We're going to get contradictions. Case 1 is where f of a is equal to 0. If this is the case, since on this part right here, if this is a, f of a is the biggest thing in this region, that means that for all of these z's, that means that f of z has to be equal to 0 because f of a is bigger than or equal to f of z. And if you have 0 equal to f of a, bigger than or equal to f of z, pretty clearly f of z has to be 0 too. So I have, for every point in here, f of z is equal to 0. So I'm just going to pick some of these points and I'm going to just make them tend to a. I'm going to call these the z sub n. Well, then what I have is that f of z sub n is equal to 0, because everything is equal to 0, which equals to the 0 function at z sub n, which is always equal to 0. So by the identity principle, f equals z on g, right? The identity principle is absurdly strong. So f is equal to z on g, so f is constant is equal to 0, which is a contradiction. So therefore, we cannot have that f of a is equal to 0. So instead, we're going to consider case 2, which f of a is not equal to 0, in which case I can define the function g of z is equal to f of z over f of a. And if I take the modulus of g of z, I'm going to get that that equals to f of z over f of a. And this top thing is less than or equal to f of a, which equals 1. So that's one thing I know, is that this modulus is always going to be at most 1. Well, what can I do next? I should also note that g of a is equal to f of whatever the input is divided by f of a, and the input is a. Oh, so g of a is equal to 1, which means that the graph of it, g of a, maps down right there. Now, f is holomorphic, so it's continuous. G is defined in terms of f in a nice way, so g is going to be continuous, which means I can find some sort of a region where g of a is always going to have a positive real part. I'm going to avoid the 0. And I want that because I'm going to take the log of it. I'm going to let h of z equal the principal log of g of z. So, in particular, you might know that h of a is equal to log of g of a equals log of 1. The principal log, that's going to be equal to 0. So I'm also going to want to take the real part of h of z, which equals the real part of log g of z, which equals the real part of natural log absolute value of g of z, plus some other stuff, right, plus I argument g of z, equals just natural log of g of z. But I know that this modulus is at most 1. Less than or equal to natural log of 1 equals 0. So this thing always has, so h of z is always less than or equal to 0, is what I can conclude. But a problem from the note says that if you have a non-constant function, so lemma that I'm going to not prove, non-constant function implies, so holomorphic, etc., implies the real part is bigger than 0 somewhere. Well, we proved that h of z is always less than or equal to 0, so the real part has to be bigger than or equal to 0 somewhere, but we proved that can't happen. This is a contradiction, so therefore f of a cannot be 0, so you can't have a maximum.